still can't hear me?
Yeah, sorry.
I can use that.
Can you?
I can use this. Okay, no problem. Yeah, I was about to say also to meet people I haven't met yet, and there are a lot of young people here, and I think it's great that we're all in the one place together and meeting new faces. So Dylan set me up for this rather ambitious thing. I can give a survey, but I realize it's pretty hard to give a survey of all geometric and algebraic methods, so I sort of settled on trying to take a little slice of some stuff that I think is exciting and I hope communicates to a wider audience at the expense of just picking something a little idiosyncratic perhaps. And some of it's well known to some people, of course. A lot of it's not totally new, but I think mostly quite promising in terms of new developments and pretty good in terms of applications as well. So here's a bit of an outline. So I want to talk about geometric things both from a convex geometry point of view, the Matroid polytope, and then also from the point of view of algebraic geometry, motivating at least some constructions that can be phrased in pure combinatorics eventually in Matroid theory. And so I want to talk about the Chow ring of a Matroid and introduce what that is at some point. Talk about valuative invariance, and then I think the thing that I want to tie it together with is that valuativity and the Chow ring of the Matroid interact in a couple of interesting and I think non-trivial ways. So let's do that. Ooh, that's too small to see, but that's the way it is with the bibliography for this subject. And I had to stop when I ran out of space, but there are a lot of papers that you can. I will mention in this talk, and I wanted to write them down somewhere. So you could ask me for my slides if you need that list. And I zip past it because you're not going to write it down. So let's have a Matroid. So it's a nice thing about a Matroid conference. Usually you have to define what is a Matroid. Well, maybe let's not do that. Let's think about Matroids from a convexity point of view by thinking of the Matroid base polytope. So there's the convex hull of the indicator vectors. I'm supposed to use my pointer. Let's see, indicator vectors, right? So for each base B, I can take an indicator vector in the Euclidean space where the basis is the ground set of the Matroid. And then I end up with something, as Gelfand, Goreski, McPherson, and Serganov observed. The edges in the polytope connecting the vertices differ by basis exchange. So the direction between them lowers one coordinate and raises another one. So then those edges are parallel to vectors ui minus uj. And it turns out that's a characterization. Any polytope whose vertices are in the unit cube and whose edges are parallel to those ui minus uj type A root direction vectors is a Matroid polytope. And of course, if you have the polytope and you know its coordinates, then you can reconstruct the Matroid. The faces of a Matroid polytope, the faces are given by taking a linear functional maybe and then looking at where it maximizes. That picks out generically just a vertex, but maybe more. Those faces are also Matroid polytopes of some degenerations of the Matroid you started with. So here I write out the little example with U24. Any two-element subset is a basis for U24. So I end up with an octahedron. Well, it's living in R4, but happily for me, I can pretend it's in R3 because in the Matroid polytope, all the coordinates add up to the rank. And so it actually lives in a hyperplane given by the sum of the coordinates equals 2. And then for fun, I pick out, if you can see in green there, a face, which is another Matroid of rank 2, where the points 1, 3, and 4 have come together. So you guys should ask me questions too, or interrupt if my examples are incoherent. Since I feel a little jet lagged, to be honest. I just came from Canada yesterday, and this is sort of the first thing I'm doing in Korea. So it's exciting, but if I don't look too smart, there's probably, I've got a good excuse. So if you have an inclusion of a Matroid polytope, one inside another, then that's the same as having a weak map from the one Matroid to the other that preserves rank. And I'd like to collect all of these faces, which are loopless. I said they were Matroid polytopes, so they have Matroids. And then the loopless ones make some kind of collection of directions, which I will call the tropicalization of the Matroid, which is non-standard, but it'll fit with today's program. So this is, for if you prefer the language that you've heard before, this is the support of the Bergman fan of the Matroid. And it's a little thing. It's generally not full dimensional because there are Matroid degenerations which do have loops. If you look back at my octahedron, you can see if I pick the opposite direction, then all those bases, we're missing the number 2, and so then that face is a Matroid where 2 is a loop, and so it would not be in my fan. And I end up just collecting the 4 rays, which are shown here in this case. So that's some kind of subfan of the normal fan of the polytope. And I'll come back to it. Okay, so the first thing, I guess, up on the table today would be this notion of valuative equivalence. And I'm going to talk a lot about Matroid invariance. So this is my angle, Maybe one aspect of Matroid theory is to, measure the wide variety of Matroid invariants which are available, and it's not just about distinguishing isomorphism. It's there's quite a bit you can learn, I argue, from Matroid invariants that are even satisfying this rather rough-looking equivalence relation of valuativity. So one way to say what that is to take the Matroids and then make a free abelian group on Matroids with fix the ground set. I'll always fix the ground set today. And then maybe also fix the rank temporarily. And think about the Matroid polytope and allow inclusion, exclusion in the space where the polytope lives. So if I did that, then I could make the Matroid polytope for U24 from some smaller Matroid polytopes that intersect along a common non-face, in fact, some Matroid polytope that lives in the interior. And so the indicator function on this octahedron, this is the function that says 1 if a point's inside and 0 if a point's not inside. Certainly, the indicator functions satisfy this linear relation. So I will say in my valuative group that the Matroids or their classes satisfy the same linear relation. So that's to say U24 is the class of these two. If I drew a graph, I guess that's a triangle with a double edge labeled in 2 different ways. And then here's a graph with 2 double edges, 1, 2, and 3, 4. And so the point of having such a thing is that an invariant of Matroids sometimes factors through this group. And we'll say the invariant is valuative if it does. So what that means is that the Matroid invariant on U24 would be the same as the invariant applied to this guy and this guy minus whatever it is on this guy. So my trivial example is that the number of bases is certainly valuative, since that's the number of vertices of the polytope, and it is going to satisfy these inclusion-exclusion relations. And so the advertisement, most people have seen these, but if you haven't seen valuative invariants, then you'd be struck by how there's actually quite a lot of them. And I should refer to a recent paper of Ferroni and Schroeter on I forget even the title. It was on that list of tiny things, but Benjamin Schroeter is here, and he can tell you about it later. The list includes, the Tott polynomial and all its specializations. The G invariant of Dirksen is a universal invariant for valuative relations. There are so-called Kazhdan-Lustig-Stanley polynomials that appeared in work of Elias, Webster, Proudfoot, and Wakefield. The Chow polynomials of Matroids. Some of these are the recent ones. More classical things might be like the Ehrhart polynomial, which enumerates the lattice points inside the Matroid polytope, is valuative. The independence complex of a Matroid has a Laplacian, and it has eigenvalues, and somehow miraculously those are given, or those satisfy valuativity. And then maybe just to advertise some possible future talks this week, there's the G polynomial of Speyer as well, which is almost valuative. I won't say what co-valuative means, but we could take it as being basically the same thing. And so Dirksen and Fink showed that those valuative relations coming from the inclusion-exclusion property in the place where the polytopes live are actually generated by Matroid polytope subdivisions. Just like I drew earlier, one way to get such a relation was to carve up a Matroid polytope into little Matroid polytopes. And it turns out that notion of weak valuativity is the same as the notion I defined, which some would call strong valuativity, and it's just all the same thing. But then there are certainly non-obvious relations, like the class of U36 then could be rewritten in terms of some of these. Sorry, I hope this notation is okay. I've got a rank 3 Matroid down there with a single triple point ijk, where that could be 1, 2, 4, 1, 3, 5, etc. So what I'm aiming for then was this relation that U36 is alternating sum of all sorts of crazy pieces, getting down to the most special one, which is the Matroid of the K4 graph, labeled like that. And then if you look at that, so there's something different going on. You don't see any subdivision, but it certainly looks like a relation that I'm taking those triple points, which are circuits. They're also hyperplanes in the Matroid, and then I'm kind of relaxing them one by one until I get down to the uniform Matroid. So that's also something that happens in this valuative group. And then I could do the same thing for some of those other bits and move stuff around. And then I could write, for example, the K4 Matroid as a linear combination of 4 of those guys with the unique hyperplane, and minus several copies of the uniform Matroid. So unlike deletion-contraction relations, which are a little bit similar, this isn't clear which way you're going. It doesn't say, I'll take a Matroid and I'll cut it up into simpler and simpler pieces until I get down to loops and co-loops. This is it got a different flavor. We could also build things up. So I took something where the Matroid polytope happens to have no dissection into 2 pieces that snap together, but I could still maybe learn about it by writing it as a linear combination of bigger things. So this, I'm illustrating by example something, a Schubert Matroid, I would say, is by definition a Matroid whose cyclic flats form a chain. So you don't have any incomparable cyclic flats. There are many other characterizations of these guys, though, right? And you probably know them. These are also called the Freedom Matroids in Crapo's original work. They're a certain kind of lattice path Matroid where there's only one non-trivial lattice path in the definition, up to isomorphism. They're They're a kind of transversal matroid where the sets and the transversal sets are nested, so sometimes they're called nested matroids. And if they're all realizable over sufficiently large fields by generic reduced row echelon matrices. So that's kind of important. They're certainly realizable. And Bonin and Demier have a couple of papers that develop the properties of these guys in depth. What? Sorry. The important thing was that the Schubert matroids form a basis for this valuative group. So up here, I already used it. The uniform matroid and those people with the single cyclic flat there, IJK, were Schubert matroids. So I've just done a decomposition of a matroid as a linear combination of Schubert matroids, which for some of you, you'd say, oh yes, and you did it also by relaxing those circuit hyperplanes one by one. And so if you said that, you would be correct, in the full details of how this goes are in this remarkable paper of Luis Ferroni and Benjamin Schroeter on the split matroids, which I will just advertise in this survey as being like a large class of matroids. Includes the paving matroids for certain. So maybe asymptotically that could be like all matroids. And they're characterized by having this property that if I do a generalization of relaxing a circuit hyperplane to make my matroid more uniform, then I can iterate that, and then I'll eventually get to uniform matroids. So you should read their paper for the real details, but I think, somebody may correct me if I'm wrong, but it means that the lattice of cyclic flats has no proper cyclic flats that are comparable. Maybe that's true. Something like that. So the point is, with these guys, it's easy to compute valuative invariance if you can compute those valuative invariants for these Schubert matroids, which usually look pretty doable. And so they showed, this gives you another proof that the coefficients of the Ehrhart polynomial need not be positive, which was a conjecture due to, I don't remember whom, but it was supported by a lot of computational evidence. But with these split matroids, you can probe a lot further and find things that are generically not true. You can make convincing counterexamples. Are there any questions about that? I think I'm about to turn the page for the moment on valuativity. Okay, so now the next ingredient is a different flavor of geometry. And so I'd like to think about the realizable matroids. And confidentially, these are my favorites, since if you hear about people studying hyperplane arrangements, what they're really doing is studying linearly realizable matroids with no loops. Because if you have such a thing, then you have non-zero vectors, and the vectors complements are hyperplanes, and sometimes a lot of interesting stuff can be obtained by looking at things like the complement of a union of hyperplanes. Okay, so the realization is a linear subspace of a n-dimensional affine space with one coordinate for each element of the ground set. And I guess we should think of it as the row space of a matrix, right? This W. A matrix of full rank up to coordinate changes in the row space, but of course not in the column space, because the column coordinates are combinatorially significant. So when you've got such a realization, like I said, you can take the intersection with the coordinate hyperplanes in the big space, and you get a hyperplane arrangement in the little space. I won't use that today, but that's a maybe topologically interesting space if I do it over the complex numbers. If I do it over the reals, then of course you draw some hyperplanes and they chop up space into connected components and you get some interesting combinatorics. If you do it over the complex numbers, you get topology. So another possibility is to consider the so-called reciprocal plane, where I take this Matroid realization, which is just a linear subspace, and then I take its coordinate-wise reciprocals, wherever those are non-zero, and then I take the closure, and I get some algebraic subvariety which has applications and some history, which I'm just mentioning these things kind of in passing, but there's the Matroid-Schubert variety. Some of these things could come up this week too, and some of them might be your old friends, so why not mention them? So this here is the closure of the Matroid realization in a product of projective lines. So the affine space gets completed to allow each of the coordinates to go to infinity at the end. And then I end up with my affine Euclidean space living in some compact box, which again could be useful. Turns out it is. There's the so-called critical point variety, which came up from an application problem about critical points of evaluations of products of linear forms to certain exponents. But we don't need to know about that. But it just gives another example of something built from a Matroid realization, also called the logarithmic conormal variety. And then maybe Alex Fink will mention this another algebraic variety which comes in handy in some exciting new work, which I can't remember if it had a name. Could I call it the diagonal Dilworth variety? Or pardon me? Okay, yeah, diagonal Dilworth it is, right? Yeah, so there's some Matroid construction which when realized, gives you a pretty interesting variety, apparently. So some of these give you algebraic constructions which impose constraints on the Matroid, and some of them are just sort of suggestions about what kinds of things to look at. So at some point we will talk about their interactions with the valuative property too in various ways. Okay, so let's see. To be a little more precise again, we've got what I will call the Matroid fan, which some would call the Bergman fan of the Matroid, is a combinatorial object in, I can't remember, you guys won't remember, so unless you saw it before, that N is just Euclidean space where I worked modulo the all ones vector. The rays are indicator vectors on flats, and the cones, I can make a cone by taking some rays and taking their non-negative real span, provided that the flats form a chain, that they're nested, non-empty proper flats. So that is some kind of manifestation of the order complex of the lattice of flats of the Matroid. But what it did for Ardila and Clivens was triangulating this tropicalization of the Matroid set, which you remember was some, I gave you some subfan of the Matroid polytopes fan with the condition that those directions picked out loopless faces of the Matroid polytope. And then the reason for this, of course, goes through some tropical geometry. If you tropicalize a linear space, this is exactly what you get. So we don't need to talk about that in this talk, just that it's in the background somewhere. And in the case of the free Matroid, every subset's a flat. And so then I'm talking about a fan where all the indicator vectors are span rays, and all of the subsets which form chains make cones. So I get a fan which is complete. Every point in the Euclidean space is in some cone. And this is called the permutahedral fan, which it turns out it's the normal fan of a polytope, the so-called permutahedron, which for some people is their favorite polytope. And then there's also this augmented version, which I'm distinguishing. If I had two screens, you'd see the difference, right? These sort of so-called classical guys have a little underline. This lives in a Euclidean space of dimension 1 lower. This augmented Matroid fan lives in the full ground set dimensional Euclidean space, and it's given by a similar recipe. I've got rays and cones, and it triangulates the free coextension of the Matroid, it turns out. So there's just some technical reasons why you'd admit these two things, but let's say they're not very different. And then in the case of the free Matroid, I get a complete fan, which is the normal fan of the stellahedron, which is, if there may be somebody in the room who'd be happy if I say it's a graph associahedron of a star-shaped graph. Yeah, if that doesn't resonate with you, then that's perfectly fine. Another one is the conormal fan of the Matroid, which lives in a double-dimensional space, which appeared in some work of mine with Federico Ardila and Junhei He. And it's a tropicalization of this logarithmic conormal variety, so another variation. So from these things, we've got some algebraic invariance. In fact, for any simplicial rational fan, I can make an algebra, the Chow ring associated to the fan. I'm skipping through the construction of a toric variety and then making a Chow ring of a toric variety. And, I mean, I can say these words, but let's concentrate on what's actually good for our discussion here. These Chow rings are finite dimensional or finite rank abelian groups. They're graded, so they're Gorenstein rings. They're commutative. The elements in degree I are given by taking subfans of the fan with appropriate weights on the subfans. So these are called the Minkowski weights. The Chow ring has a intersection product given by tropically intersecting subfans. So it's a combinatorial device, and I can do it for Matroids by feeding it the Matroid fan. So let us say that the Chow ring of a Matroid is just this Chow ring, which I did not actually define for you, of the Matroid fan. But it's perfectly possible to write it as a quotient of a polynomial ring modulo some easy combinatorial relations. So I could work with it hands-on algebraically if necessary. I've got one generator for each flat, and then some linear relations and some quadratic relations. And then likewise for the augmented fan, I could make the augmented Chow ring. I can make the Chow ring of the conormal variety. And well, let's taken together, let's see if these are useful for something. So their degrees make polynomials because they're only finitely many non-zero degrees given by something like the rank of the Matroid or the size of the ground set. And it turns out that those Chow polynomials are, again, valuative invariants. Well, I haven't sold you on these yet. We need a use, right? So they've got, for some magic reasons, their top non-zero piece of the ring is isomorphic to the integers by a so-called degree map. And maybe the other thing that we could say is that for the free Matroid, that's an interesting special case. The Chow ring of the permutahedron, say, has inside some special Minkowski weights given by saying that those Matroid fans were subfans of the permutahedral fan that I mentioned. And if I put weight 1 all over them, then it turns out those are Minkowski weights. So each Matroid with a fixed ground set gives me a class and a Chow ring. the Chow rings contain some numerical data. If I look at the characteristic polynomial of the matroid, or its shift, then I get some coefficients which, if I toggle the signs, I can make all non-negative. And I guess, one of these things gives me the coefficients of the Tut polynomial if I set the second variable equal to 0. And the other thing gives me something obtained from that by a minor change of variables. So these are the, if you prefer, the F vector and the H vector of the broken circuit complex of the matroid. I can mention this Chow ring of the matroid sees these numbers. So you can find classes in degree 1 where if I multiply them up to top degree, which is some one-dimensional thing, and then take the degree map, I get numbers. And you can show that these numbers are these coefficients. There's also the question about the Whitney numbers of, I think it's the first kind in the geometric lattice, or the lattice of flats of the matroid. Let's let Li be the set of flats of rank I. So this Dowling-Wilson conjecture stated that the number of flats of a matroid of rank I was bounded above by the number of flats of rank J, where J was bigger than I, but not bigger than rank minus I. So this was not just a conjecture that these numbers were unimodal, but that the bigger ones were bigger than the smaller ones read from the inside out. So if you haven't seen this before, then I should have drawn a picture, but I'm gambling that most people would have seen this conjecture, which is best discussed in rank 3, just to start. Then we're saying that the number of points in a configuration is less than or equal to the number of lines. And these are captured by the degrees of some algebra, the so-called graded Möbius algebra, almost tautologically. I just make a vector space with one vector for each flat, and then there's some multiplication rule given by taking a pair of flats to their join in the lattice, provided the join is in the right rank and otherwise 0. So this graded Möbius algebra then absorbs the Dowling-Wilson conjecture as something about its algebraic structure. But it's a little weak. It doesn't really tell you the answer. It lives inside the Chow ring of the matroid as a summand. That's the augmented Chow ring. And now we're coming to this rather extensive and exciting work of Braden, He, Mathern, Proudfoot, and Wang in 2 papers. I really can't do justice to it, but I just want to point it to you. As matroid theorists, you should really have a look at this if you haven't already. So they find algebraic structure behind this purely combinatorial conjecture. And in the realizable case, one can find answers. These Chow rings are really nice algebras in the realizable case because they line up with the cohomology algebras of complex, smooth manifolds. So then one can study the Chow ring in more depth. And again, I know many of you have been to talks about this before, and I apologize if you've heard it too many times, but it's a useful tool. So I think it's worth slipping in here, even if I have to move a little bit quickly on it. These Chow rings are examples of graded Artinian algebras with these so-called Lefschetz properties, which are Poincare duality, which is an isomorphism between the degree I piece and the degree R minus I piece. D, sorry, where D is the top non-zero degree you see in the algebra. The Poincare duality isomorphisms are a little bit richer because they're actually achieved by multiplication by certain elements. So if I take elements of degree 1 in a graded algebra and multiply, the degree goes up. And if I look at complementary degrees, these degrees were supposed to form a palindromic sequence, so the degree k piece had the same dimension as the degree d minus k piece. And the hard-Lefschetz property says that this isomorphism is actually achieved by just multiplying in the ring. And then the third property is the most delicate. This Hodge-Riemann property says that if I multiply two classes in the same degree and then top up with a few degree 1 elements until I get to the top degree, then that's a one-dimensional space. And Poincare duality tells you you can turn it into a number. So if I did that, I would have a symmetric bilinear form. And the Hodge-Riemann condition is that the bilinear form has a certain signature, which I shouldn't write like this. That's opaque. But I prefer this picture. So if you look at the Lefschetz properties, you should think of your graded pieces of the algebra A with the grading going up from left to right, and the dimension of each piece being the height of my little stacked column here. So each of these pieces are finite dimensional real vector spaces. So Poincare duality says that it's symmetric under the mirror image in the y-axis. Hard-Lefschetz says that the symmetry is achieved by multiplication as an isomorphism. And then Hodge-Riemann says that if I make a bilinear form on one of these pieces on the left half of the picture, that the signature is predictable. And the signature is supposed to go like I show in the little boxes, plus, minus, et cetera. So then if you pick a particular degree like 0, 1, 2, 3, 4, then your signature is something you can compute. And so then you could use that if you knew you had these properties. For example, I've got this free choice of L, this product of degree 1 elements, which gives me, in degree 1, some inner product which satisfies backwards Cauchy-Schwarz inequality. And then if you pick the right L, you can use your backwards Cauchy-Schwarz inequality to show that we saw that these FIs were degrees of products of certain alphas and betas in the Chow ring. So that lets Adiprosito, He, and Katz conclude that the coefficients of the characteristic polynomial satisfy these log concave inequalities. And then likewise, for the H vector of the broken circuit complex. So some geometric constraints give you combinatorial inequalities. Let's see. Likewise with the Dowling-Wilson conjecture, these authors show that the conjecture is true. So that's a nice thing. And then what they have to do is, again, uses the augmented Chow ring of the Matroid to pull it off. We had this graded Mobius algebra. Remember that guy? So this was the one who knew about the number of flats of each rank. And it lives inside, I said it was a summand of the augmented Chow ring of the Matroid. So far, so good. Well, this augmented Chow ring of the Matroid, it turns out, does have these Lefschetz properties. So this is something you have to prove. It's not enough. They have to insert some other object inspired by geometry. You need the so-called intersection cohomology of the Matroid, which is drawn from the actual intersection cohomology of the Matroid Schubert variety. Now you'll say, there was Schubert Matroids, there's the Matroid Schubert variety, what's going on? So this was the thing you got by taking the closure of a linear realization in the product of P1s. So it was some actual variety whose properties, it turns out, miraculously carry over to all Matroids. So this is what these authors show, that the inspiration from plane geometry actually gives you something that you need new techniques to do, but you can do. So some old conjectures could turn into things you could show about chow rings of matroids. Okay, so let's loop it back to valuativity, since maybe there was enough of that. I meant to put pauses in my slides, so you shouldn't look at the bottom, but I can't cover it up with my hand because the screen's too big, but that's life. So let's take a variation on this valuative group. The little underline means reduce modulo the all ones vector, but in this business it also seems to mean forget about the matroids that have loops. So let's take the indicator vectors of the loopless matroid polytopes. So this is the only word where this differs from the valuative group we had before. And what for me I find still a rather remarkable result, that these valuative groups, if you fix the ground set and you sum them all together for all ranks, let's see. So if you fix the ground set, certainly the matroids of rank I are in bijection with the matroids of rank R minus I via matroid duality. So that's okay. So there's some kind of palindromicity in the numbers of matroids, but it turns out there's also palindromicity in the number of matroids modulo valuative equivalents. Well, more than that, if I take all the matroids modulo valuative equivalents with no loops, that is the chow ring of the permutahedron. So I had some graded Artinian algebra with magic properties for the free matroid, and then that's actually, all the valuative groups for a fixed ground set. So this was Simon Hampe in this paper, Intersection Theory for Matroids, in 2017. And then in some ways, it's actually, there's a good reason for suspecting that. You take a matroid to the Minkowski weight given by its matroid fan, and that matroid fan is a subfan of the permutahedral fan. I tried to sell that point. So that must be a class in this chow ring, and it's, this map is well defined. The valuative identities get sent to 0. Well, it turns out it's actually an isomorphism. That's additive structure, but the chow ring has a product. It's a ring. One way to get your hands on that is by intersecting fans. This was this Minkowski weight interpretation. And it turns out when I intersect Bergman fans on the matroids modulo valuativity side, that turns into matroid intersection, which is the dual to matroid union. I guess the intersection of two matroids on the same ground set is, by definition, the matroid whose bases are intersection of bases, provided that their size is what you think it should be, and otherwise 0. So this makes a graded ring, and this is the chow ring again. Let's see. So we also know that the valuative group had a integer basis given by Schubert matroids. And then this variation here with the loopless business has a basis given by the loopless Schubert matroids. And then it turns out that these are counted by Eulerian numbers, and there's some lovely combinatorics in the permutahedral fan now that we have a basis for its chow ring in terms of Schubert matroids. Let's see. Well, yeah, maybe it's kind of not too pleasant to disallow matroids with loops unless you don't like loops or something. So in a more recent paper, Chris Uhr, June He, and Matt Larson showed the augmented version, the augmented chow ring of the free matroid was this stellahedral ring. And they showed that the analogous result holds. This is the valuative group for all the matroids, never mind loopless. And then it makes the grading actually work out a little bit. more nicely. Sometimes this augmented version is actually better. So what? Well, let's see. So a valuative invariant, like say the Tut polynomial, then is a function on the valuative group that preserves the valuative relations. So Poincare duality says that every function on this valuative group is given by a pairing. So the Poincare duality identifies a space with its dual. So the Tut polynomial then is a linear combination of matroids. There's for every valuative invariant, there's some element here which intersecting with that element is your invariant, which I think is kind of cool. So the classroom exercise here then is to say, so we had the level 0 valuative invariant, which was to count the number of bases of your matroid. Not too impressive, but it's a good starter invariant. Suppose I do that. How do I count the number of bases by an intersection product? So I need a matroid. If I want to do it for matroids of rank R, what I need to do is come up with a single matroid of rank n minus R, so that when I take the matroid intersection with this M, I get something, a matroid of rank 0, and the number of times I want to see it is the number of bases. So that's what this really means. So you can ask me later if you're curious. Maybe in my last few minutes here, I want to squeeze in one more geometrically motivated construction. So maybe we'll sort of skim the surface of this. But once again, so this is work of Birgit, Ur, Spink, and Seng, which I think it will have lots of further applications. But once again, motivated by a matroid realization, say, I think over the complex numbers to be safe, I can make a vector bundle on the Grassmannian. And if you'd rather not think about that, then you don't have to. I'll just say it's a rank R vector bundle, some object that's a subbundle of a trivial bundle, so it has a quotient. So the realization determines a bundle S and a quotient Q of complementary dimension. But then we can forget about them because they have invariants in K-theory and the Chow ring of the stellahedron, or the permutahedron in this case, which are just combinatorics. So it's a black box. And if I apply the black box, I get some elements of the ring, which I can bundle up in some kind of either gorgeous or terrifying generating function, where I take all the degrees of alpha and beta were some kind of degree 1 classes that were not very interesting, but if I multiply some alphas and some betas and some Chern classes from these bundles to get to the top degree and apply the degree map, then I get a number. So I get some integer coefficient of x to the I, y to the j, z to the k, w to the l, and I add it all up, and it turns out that what I get is some, housekeeping term times an evaluation of the Tut polynomial, which in the realizable case. And they had a reason for this. They want to do something about the Tut polynomial. To keep it on the screen, I just copied that over again. The real point here is that their geometric construction survives for all matroids. So that whatever they did with vector bundles, actually the combinatorial formulas you get have the same formal properties for all matroids, even if they're not realizable. And the trick is that in this Chow ring of this permutahedron, we saw that the relations in there are valuative. So in a sense, all you have to do is notice that their realizable formula works for the Schubert matroids, and then extend linearly. Then their formula works for all matroids. So this seems to be a good trick. The valuative invariance can let you write a non-realizable matroid as a linear combination of realizable ones. And so if you could do something geometric with realizable matroids, then you may be able to extend it, as they did. So they conclude with this clever valuative trick that for any matroid, the coefficients of some reparameterization of the Tut polynomial into some array where there's really only two directions in this array, really. It's a two-variable polynomial. But repackaged suitably, they can find that in all directions, we see log concave sequences of integers. Again, using the Hodge theory for matroids. So that's probably almost the place to stop. I wanted to close it by saying that in some way that I don't think we fully understand these valuative equivalences on matroids tie together with geometry coming from this tropical varieties, toric constructions, intersection theory, in some way that all amounts to combinatorics at the end. And I think it forms a promising foundation for future work on at least Matroid invariance, but hopefully, I'm sure, I know there are a lot of people here who are interested not so much in Matroid invariance and something else. So I hope also for something further. So at that, I'll stop. Thanks.
Okay, so we have a coffee break now, and I think in the interests of having enough time for coffee, we might just say that questions for Graham will take place during coffee. Does that sound okay? Okay, unless there's one very quick question before we go to coffee. Okay, so we'll save questions for the coffee break, and we will be back here in 15 minutes, 5 minutes to 11 is when we start. 10:55 restart. Thanks, everyone.